Let's end class today by just doing an overview of various classification theorems. That is the goal of being a group theorist, is to classify and understand groups. So what are some of our classification theorems? Our first classification theorems came in chapter 7 on Lagrange's theorem. And the very first one was a corollary of Lagrange's theorem. Every group of prime order is isomorphic to ZP. Every group of prime order is cyclic of order P. Or every group of prime order P is cyclic of order P. Doesn't mean it equals ZP. Could be a different group as far as what its elements are and what its operation is, but it's going to be isomorphic to ZP. So from a group theorist perspective, it's the same as ZP, even though it's technically not equal. It has the same structure, the same Cayley table. You can make the Cayley tables match. Our next classification theorem is this one. Let G be a group of order 2P where P is a prime greater than 2. Then G is either isomorphic to Z2P or DP. In other words, it's either cyclic or it's isomorphic to a dihedral group of order 2P. Right, we only put a subscript of P there because this is referring to symmetries of a regular P-gon. 5-gon would be a regular 5-gon would be a regular pentagon. 3-gon, of course, would be an equilateral triangle. 7-gon, what's that called? Septagon, maybe? Septagon? 7, I'm focusing on primes here. 11, I don't know what it's called. Regular 11-gon having equal sides, 11 equal sides and 11 equal angles. What are the symmetries of that? It would be D11, which would have 22 elements, 11 rotations, one of those rotations being the identity that does nothing, and 11 reflections or flips. In chapter 8, we saw, as an example, example 3, what about groups of order 4, 2 times 2? Prime 2. Then you get either cyclic or isomorphic to the external direct product of Z2 with itself, also known as the Klein 4 group, which can be written in a purely abstract form as well. The book writes it as E, A, B, and AB. I wrote it as E, A, B, and C a week or so ago. All the non-identity elements have order 2. It is an abelian group, as opposed to the case we just looked at a minute ago, groups of order 2P where P is a prime bigger than 2. DP is not abelian. We shouldn't call this D2 because there's no such thing as a regular 2-gon. Right? No such thing. It is abelian, though. More classification theorems come. Let's see, I forgot. Is it chapter 9 or chapter 10? Well, you got your facts about U groups and how they can be external direct products of cyclic groups. That's not really a classification theorem in general, though. It's a classification of U groups. This is a partial classification theorem. It's a classification of finite abelian groups whose orders are products of primes to first powers, distinct primes to first powers. Square-free order. So the prime factorization doesn't have any squares in it, is the idea. So a group of order 2 times 3 times 5, 30 would fit this. A group of order 2 times 5 times 7, 70 would fit this. A group of order 2 squared times 3, 12 does not fit this. If you know your abelian group is of order, this kind of product where you've got distinct primes to first powers, then it's got to be cyclic. And that should make sense. The GCD of those things would all be 1. Go back to thinking about external direct products, the external direct product of, for example, Z3 with Z4 is isomorphic to Z12, because 3 and 4 are relatively prime, although that doesn't fit this because 4 is 2 squared. But that is a specialized one because you're assuming it's abelian. This does not apply to non-abelian. This one is about classifying groups of order p squared where p is prime. It's isomorphic to either zp squared or the external direct product of zp with itself. So it's abelian. Any group of order p squared where p is a prime is abelian. Any group of order 49 is abelian. Any group of order 121 is abelian. In fact, there's only two possibilities for what it is isomorphic to. Yeah, a corollary of that is any group of order p squared where p is prime is abelian. So these are classification theorems. Chapter 11, which I said we might get a tiny bit to before the exam on Monday. Well, the exam's Wednesday. On Monday, we might talk about chapter 11 a tiny bit. I'm not sure. It's a hard chapter, as all these are. Say it's harder. So if it's on the test, it would be just the most basic ideas of it. Okay. Have a good day.